right. So we proceed our morning session with a talk by David Favero from University of Alberta, and who is going to tell us about what is this? So I can't read.
CoFTs for GLSMs.
All right. Okay, David.
Yeah. So there's almost no words in my title, which makes it especially confusing. So I'm going to talk about cohomological field theories from gauged linear sigma models. And this is joint work with Bumsig Kim and Chiakan Fontenine, Guerra, Kim, and Shoemaker. So Kim is the same Kim, Bumsig, but these are two different papers that I'm going to talk about. So, okay. So I don't have all my notes set up. I only have the table of contents here. So I'm going to talk about, contrary to my title, I'm going to talk about these in reverse order. First I'm going to talk about GLSMs, then cohomological field theories, a little bit of history of constructing cohomological field theories for GLSMs, and then a sketch of the most recent construction with Bumsig Kim. Okay. So GLSMs. All right, so I'll be a little sloppy here, and I'll say that a GLSM is the following data. So you have G is going to be a reductive group. V is going to be a G representation. Theta is going to be a character of that group. And W, I'm going to work over C, okay? And W is a polynomial function. And so if I was precise, it's a little more intricate than this, but this is the basic idea. So this data gives you a GIT quotient with a function to C star. So you get this Landau-Ginzburg model where the space for the Landau-Ginzburg model is a GIT quotient. Okay, and then I'm going to assume, this is by definition, that one, the critical locus is proper, and two, the semi-stable locus agrees with the stable locus. So this implies that this GIT quotient is a smooth DM stack. Okay. And then the critical locus is some nice proper thing inside of it. Okay, so I'll do a basic example for motivation. Sure, many of you have seen this. So let's let C star act on C to the n plus 2 with weights 1, 1 minus d. Okay, I'll call these variables x, 0 through xn, and this variable is going to be called p. Then A, I'll have two different choices of character. One is C star to C star by the identity, and two is C star to C star by inversion, so T goes to T inverse. Okay, and I'm going to let f of x is any homogeneous polynomial. Well, maybe I shouldn't say any. I'll say a homogeneous polynomial of degree d. I could probably say any here since I'm not making any statement, but I'm going to want it to have an isolated singularity at the origin. So then I'll define W to be P times f of x. Okay. Then A, if I look at this GIT quotient, this is the total space of O of minus D over Pn. Okay, and the function is pairing with f. Okay, and then I'll talk more about this, but so the enumerative theory for this GLSM is going to correspond to Gromov-Witten theory of the hypersurface, this degree D hypersurface in Pn. And if I look at the minus, oh, so I should say, please turn on your audio and interrupt me at any point. This is pretty informal, okay? So if I look at the minus GIT quotient, this just becomes C to the n plus 1 mod z mod cyclic group of order D. You know, this isn't uniform notation, but I always like to write it this way. Okay, and the function is just the function itself. It's just f. Sorry, maybe my notation's a little bad. W restricts to, and under this identification, W restricts to just f. Okay. So, e.g., n equals 4, d equals 5, you get, oh, I should have said, sorry, before I go to my example. So this thing is FJRW theory of f. Okay. So, for example, if you do n equals 4, d equals 5, then the two theory, A is Gromov-Witten theory of the quintic. And B is FJRW theory of the quintic. And as Matt mentioned yesterday, these are related by analytic continuation. Okay. And so this was Chiodo, Iritani, Ruan. And another example, n equals 4, sorry, n equals 5, d equals 4. A is Gromov-Witten theory of the cubic, and B is the FJRW theory of the Kuznetsov component. So anyway, that was just some motivation. So in general, you can get Gromov-Witten theory of complete intersections.
Sorry, can I interrupt you for a second?
Uh-huh.
About this last statement.
Yeah,
What exactly do you mean by the FJRW theory of the Kuznetsov component?
I don't. I just mean the cubic. That's a good question. I'm moving off of Matt's talk where he was trying to motivate something like this. But I don't have anything precise. Like I don't know how to compare this to Gromov-Witten theory of a K3, for example, which is trivial.
No, but that's not what I was trying to ask. Somehow, in my mind, the Kuznetsov component is something that's B-model. It's about you take the derived category of something and throw away some pieces, and you're left with a smaller triangulated category, which came from a derived category.
Yeah, but I'm just saying that the Kuznetsov component is the Landau-Ginzburg model. It is the derived category of the Landau-Ginzburg model.
Right, but it's a derived category. It's not a Fukaya category. While FJRW
right, this is A side. Yeah, it's true. But so I guess I refer you to Matt's talk. There's no precise. It's just FJRW theory of the cubic, but there's a desire via some, path to connect it to also a K3. In this case, that would mean that it should be trivial in some sense.
Okay, thank you.
But yeah, you're absolutely right. Okay. So in general, you can get Gromov-Witten theory of complete intersections in toric varieties. Grassmannians, etc. Okay. So now that was GLSMs. I'm on to section 2, which was cohomological field theories. So definition, which goes back to Kontsevich, Manin. So H is a graded vector space. Coming together with a supercommutative pairing. And a unit, so a distinguished element. Sorry, I changed the notation of this H. It's called the unit, just some distinguished element called the unit. And the main thing is for any G R, a collection of maps. So these are real numbers. Collection of maps to the cohomology of MGR bar. Okay, and then I'm just going to say satisfying natural axioms. parentheses, permutation invariants. I'm going to tell you precisely the ones we actually did, which was tree, loop, getting tails. And so then I'll do an example. Is that if Z is a smooth variety, then I want H to be the cohomology of Z. And we have the Kunath formula. And then this can go by some evaluation map to the cohomology of M of Z. So this M of Z, this is going to be some kind of moduli space of maps from I'll just say maps to X, to Z, sorry. Maps to Z from curves, okay? And then you cap with some kind of virtual class. And then you push forward by the forgetful map, and you wind up here. So this moduli space is keeping track of R marked curves mapping into Z of genus G. Okay. And so this thing here is gamma GR. This is Gromov-Witten theory. So this was example 1. Example 2 is that G is a finite group finite abelian group acting on AN. And then you get H, acting on a vector space, V. H is sum over G and G, Jacobian, restricted to the fixed locus. The sum of Jacobians restricted to the fixed, of the superpotential restricted to the fixed loci of all the G invariants. And so there's some, which I'll describe in more detail in a moment. There's something here called FJRW theory. So instead of describing that, I'll set that up in the general case. So the general case for GLSMs. That's what I mean by general. Is you let the inertia stack, so is going to be the sum over conjugacy classes of G. Sorry, there shouldn't be brackets around there. Of this quotient stack. Or here I just mean semi-stable mod, the centralizer of G. And H is the hypercohomology on the inertia stack of the twisted de Rham complex. Sorry, the twisted Hodge complex. Okay. And I'm going to call this thing, for short, I'm going to call this thing H star of something. This is just a sub W. Okay. So the idea in the general case is you start with this state space here, which is twisted Hodge cohomology. You, just like in Gromov-Witten theory, you can send it up to some kind of moduli space, which I'll get into more detail later. But you look at twisted, still twisted Hodge cohomology on that moduli space, and then you remove that. And one other thing happens. You land in the cohomology with support on the critical locus, maps to the critical locus. And that's proper over MGR bar, so you still have a push forward. Okay, and what goes here is some kind of virtual class. Sorry, it keeps turning on the eraser here. Some sort of virtual class which lives in with the minus sign. So when I cap these two together, the W's cancel out, and in some sense I get a 0 here. Okay, and that's just usual Hodge cohomology, which goes down. Okay, so any questions? So we want to construct this. All right. So I'll put a remark. Is that if V mod theta G is the total space of a bundle, W is the pairing with a section where S is a section of the dual bundle, then this twisted Hodge complex is actually quasi-isomorphic to the Hodge complex on the 0 set, and I should assume S is regular for this. And there's a shift. Okay. So that of course implies the homology. This twisted, the cohomology of this Landau-Ginzburg model is the same up to a shift. So this is called the geometric phase of the GLSM. Okay. Okay. So now I'm into part 3. History. Go away, Siri. Okay. So I talked about first case was one. G is a finite abelian group. Okay. So this is history of GLSMs, enumerative theories. Of GLSMs. So remember that was V, V, G, theta, W. Okay, so G is a finite group, which means theta is trivial. Okay. Then this was done by Jarvis, Ruan, 2013. This is FJRW theory. And there was an algebraic version doing to Polishchuk. Feintraub, 2016. Algebraic version. So I should actually move this. This all is FJRW theory. There's some different versions. So originally Fon, Jarvis, and Ruan, then an algebraic version, and there was mostly topological and the version, and then and they prove it forms a CoFT, cohomological field theory. This was Kim, Lee, 2019. And then so then there was a general GLSM version. So general GLSMs now. So one was the narrow sector case. I'll just put it this way, consistent. So this is again Fon, Jarvis, Ruan. Now in 2018, but this was narrow sector only. So this means it's missing, i.e., it's missing a primitive cohomology in the state space, or in this language, they say insertion. Okay. So H is not, it's just the pullback of hyperperforming classes. And then the convex hybrid model case, I'm not going to tell you what those words mean. but it's basically total space of a bundle with some additional construction. Oh, sorry. I want to be consistent here. So this was Chiakan, 5 to 9. That's one person. And myself, Jamie Guerre, Bumsig Kim, and Mark Shoemaker. And this was also 2018. And this was convex hybrid model case, but includes primitive cohomology, which are called broad sectors. So everything. Okay. And finally, the general case. It's from 2020, fully general. Fully general meaning with the assumptions I made on a GLSM, but just that, you have a smooth proper, you have a proper critical locus and a smooth Lee-Mumford stack as your GIG equation.
Sorry, can I ask quickly?
Yeah.
I was under the impression that the FJRW theory could still not properly be defined for groups, for abelian groups that were either, I don't remember if it was either G max or G.
Oh, yeah. So if I go back here, yeah, maybe not all, or maybe it's just some back when it was defined.
So what's the current status? That's my question. Can you now handle FJRW theory for any group in between the G max and the G?
Yeah, it's GMAT. Yeah, I don't think that that's a problem whatsoever. As long as you have an isolated singularity, and yeah, any group should be fine.
Okay, one more question. I don't remember exactly, but does the CoFT encapsulate all the higher genus Gromov-Witten invariants or only genus 0?
Higher genus, yes, all genus.
Okay.
Oh, sorry. Oh, does the CoFT? Sorry, I misunderstood your question.
Yes.
I believe the answer is only genus 0, but.
So my question is there a definition of positive genus Gromov-Witten FJRW invariants for arbitrary group in the isolated singularity case?
Yes, I'm saying now there is, and for arbitrary genus.
Okay.
Yes, but I don't know if that means it recovers, if the CoFT recovers this theory, yeah.
So your construction gives both a construction of FJRW theory and of the CoFT.
Yes. So I'm about to say a theorem, and I'll make some caveats a little bit. Okay.
All right. Sorry for interrupting.
No. Those are great questions. It's nice to know someone's listening virtually here. So yeah, let me say more, and then you can see if that clarifies your question. So theorem. So this was in this older paper from 2018. When when G is finite, this recovers FJRW theory. And then when V mod theta G equals total space of E over X, and W is pairing with the section, this recovers Gromov-Witten theory. And you can also let W equal 0 and the GIT quotient be proper and get Gromov-Witten theory. The S is section. Okay. But as actually, with the caveat that as defined by the Chang-Lee virtual cycle, and at the time it wasn't known if that agreed with the Baron-Fontecchi cycle, but that was then also proven by Kim and O. Bumsig again followed up with this by proving so this is 2018. This was also 2018. The Chang-Lee virtual cycle agrees with the Baron-Fontecchi. Virtual cycle, which is the classic one used to define Gromov-Witten theory. And then so then our theorem from 2020 is that there exists a general construction of these maps for any GLSM, or by for any, I mean, by definition, proper critical locus and Deligne-Mumford GIT quotient. Then, and furthermore, this collection of maps form a CoFT for any GLSM. So I think that's what you were asking. And now the caveat, which I think you were also getting at, is that it's not yet proven that this new construction agrees with the construction we made in 2018. They're quite similar, but there's some kind of technical things that would need to happen, like an HKR map in this level of generality and things like that, in order to actually compare them, since they're defined slightly differently. Okay, and so this new construction, strictly speaking, it's not known to agree with Gromov-Witten theory and FJRW theory at the moment. But I would strongly conjecture, and I mean, this is almost, it probably is not, hopefully is not too difficult to prove that this does agree with the previous construction, and hence with FJRW theory, with Gromov-Witten theory, and it does give a CoFT. So it should be giving the same one. Okay, so hopefully that answered your question. So I'm on to section 4. I have 20 minutes. So I'm going to talk about the idea of the construction. So this is the technical part of the talk. So we had this moduli space So we have this moduli space of maps. What we actually do, it has an evaluation map down to some space. Maybe I should, instead of X, maybe I should put the mod theta G. And here we have again the mod theta G. And forgetful map to MGR bar. Okay, and we're going to embed this in some space that I'll call A, which depends on G and R. Such that these maps extend to the embedding. So this is what we actually do. I gave you some kind of sketch, and this is what we actually do. And then the idea is we're going to find a matrix factorization. So it's like a virtual matrix factorization, K, on A, living on A, but supported on the moduli space of maps to the critical locus. And this is proper. It's a proper stack. Okay, and Lee Mumford stack, yeah. But not smooth. And then the virtual cycle will be roughly the Todd class of something. This is to be explained. Times the Atiyah class of this matrix factorization. And that's going to live, I should say this is some kind of localized Atiyah class, so that it lives in the cohomology with support on maps to the critical locus of this A. And so actually all these things are to be explained, K, A, and B. And sorry, and there's an ev. This thing lives in the twisted cohomology, the twisted Hodge cohomology with respect to this map, this function. Okay, so how to build A. So I can only say a little bit here. So I denote by bun G is going to be curves, markings, a principal bundle, and kappa. Okay, that's the data. So this is C is a curve. Q is R marked points. T is a principal, the G principal G bundle. It's actually, so I didn't actually a gamma bundle. I didn't explain what gamma was when I set up the GLSM data, but it's essentially a principal G bundle. There's this other thing called R charge that comes in that I'm not going to talk about. And kappa actually has to do with that too. It's an isomorphism from omega C log to C of some, the principal bundle. C chi. This is some. Chi is a character from such that G. So anyway, there's some data. And above it, I have the universal curve. And above that, I have the universal principal bundle. And I'll call this map from the universal curve down pi. Okay? Then I can take R pi star of this this universal vector bundle is defined as you take the principal bundle, you cross it with the vector space, and you quotient. Let's say by G. Okay. So this has a two-term resolution. And so now over bun G, you can take the total space of A. Okay. And over that, you call this map down P. You have the total space of B living over that, okay? And then that bundle has a section given by this differential, D, in this two-term complex. So that's called beta, which is the differential composed with the tautological bundle on A. And there's a co-section called alpha, which comes from W. And I'll say maybe a little bit about that. Okay, and so then inside here, you have the zero set of beta. So now if you think about what this is, yeah, I know what happened. I lost one page of my notes. So inside here, you have the, if you think about what this is, the zero set of beta becomes the data of C, Q, K, and also a section of this bundle. Because the zero set of beta corresponds to sections of A which vanish, which is H naught of this bundle. Okay. So you get this data, and this is called quasimap theory. This is maps. This is the moduli space of maps from curve into V on G. Okay, and then now consider an open set in A, in total space of A, defined by stability of curves and forcing maps to factor through the mod theta to the GIT quotient. The stacky GIT quotient. Okay. So that's our space A. And on it lives we have the following thing. So A, which is A is really an open subset of the total space of A. But on it lives a matrix factorization described in the following way. So you take, if you look at the structure sheaf of the total space of A, this had this map B, beta. This section of P star B, this was called beta was D composed with tot, where R pi star of this principal bundle was equal to A goes by D. And then it had a cosection which I didn't explain. O tot A. Okay. So then you can form this matrix factorization. It's like this: wedge even B star B dual goes back and forth by wedge odd B star B dual. And the differential is contracting with beta and wedging with alpha. So this is called a Cohomological factorization. Okay. So I got 5 minutes. So let me just tell you what the problem is. So okay, actually, before I describe the problem, well, yeah, no. So this would be it. This would be our factorization, and then we just take its Atiyah class and do some Todd correction. The Todd class of B was precisely this B, so we correct it by the Todd class of this B. We take its Atiyah class, and we're done. That's our virtual cycle. The problem is that in general, I didn't describe how to construct alpha, and in general, one can't. So in general, W only gives a map in the derived category from, I'm going to be a little bit sketchy here. So basically, alpha is a map from sim A dual shifted by 1 to sim B dual to A dual. So, but this exists in the derived category. You can construct it from W, but it may not be realizable at the chain level. So what you want to actually get a cosection, you'd write this out at the chain level like this. You expand these complexes. And so this map at the chain level, this chain realization is what you really want for alpha. And then you have to prove this construction is independent of the chain realization and all these kinds of things. And independent of the choice of resolution, and there's lots to check. Okay, so what's the solution? So in the previous paper, we were able to construct this alpha under this assumption of being a convex hybrid model, but in general, one cannot. But the solution is the following idea. So if X is a DM stack and A is a sheaf of CDGAs over OX, and W is a section of that sheaf. Sorry, W is a global function on the space. And alpha is a degree minus one element of the sheaf of algebras. Then such that, so this sheaf of CGAs has differential D, or you could just talk about a CDGA. You don't have to talk about sheaf language for this. But the idea is that if you look at, then you can form a matrix factorization. So I'm just talking about in complete generality here. So where you just take the even part of that CDGA and you go to the odd part, where the differential is the previous differential on the CDGA plus wedge alpha. And I should have said, and I require that D of alpha is W. So it's a matrix factorization of D of alpha, but I can call that some W. Okay. So then the Leibniz rule, graded Leibniz rule, implies delta squared W. Okay. So so now to get alpha in general, consider the sheaf of CDGAs given by the Cajole complex on beta and replace kappa of beta by a gamma acyclic quasi-isomorphic sheaf of CDGAs. Okay, so then this is obtained in our paper by taking the go-to-mole resolution. We need this because our moduli stacks need not even be separated. So we just take a very, very abstract resolution. This is cosimplicial. And it loses the CDGA structure. But then you can apply the Tom Sullivan construction. To a cosimplicial CDGA, and this will recover a sheaf of CD. Then after applying these two constructions, you'll get a sheaf of CDGAs again. Okay, and then the point was, if I go back up here, so now this thing has been replaced by a Flask sheaf of CDGAs. Okay, so then this map alpha is always on the total space of A. This map alpha is always realizable at the chain level. So then you can construct a matrix factorization by this construction there, for this replacement. Okay, That's it.
Questions?
Get rid of theta.
Get rid of theta?
Yeah.
You mean, can you construct like a enumerative theory on the Artin stack?
Yes. I know examples where this is done with some assumptions on the action itself, but certainly not in this generality or anything close to this generality.
So the one thing I can say is that the moduli stacks will be really bad. But this construction deals with really bad, pretty bad moduli stacks already. So maybe I don't know. And, yeah.
And then related, as you change theta, can you describe in some precise fashion how the omega GRs vary?
So that would be really nice. Of course, we expect that there's some kind of, well, you know, there's some kind of stringy Kähler moduli space or whatever, and you move along it and you analytically continue from one theory to the other, you know, or, you know, more generally, you know, if some parameter is changing, like if you're in the cubic case or something like that, there's a what analytic it's not analytic continuation, it's I forget, but there's papers by Shoemaker and stuff like this where they do the Fano case, and you still get some kind of relationship between the generating functions.
And one more question. Is there some type of mirror statement for the ring you get out of the CoFT and some other B-side ring?
So that's a good question. Hopefully, but we do not have such a statement, and I don't think anything's understood at the moment.
Okay, thank you very much.
Thank you.
I had one question too.
Yep.
Is there some understanding? So somehow my understanding of this GLSM procedure is that you're taking limits. So the two different extreme cases, the GW theory and the FJRW theory, are really two limits of a parameter that you can move to plus infinity or minus infinity or something of that sort, or zero.
Yes.
On the other hand, on the B model side, kind of there are results which say that you're doing, on one side, you're doing the calculation at some kind of large complex structure limit point, or the mirror of the Gromov-Witten theory. But at the other end, when you're trying to find the mirror of the FJRW theory, you're computing somewhere inside the middle of the moduli space at the Landau-Ginzburg point. Is there some understanding why in the B model you do not get another very degenerate situation?
I don't think I quite understood the question. Sorry. You're saying, yeah.
So the GLSM thing gives you some kind of a path from the Gromov-Witten theory and the FJRW theory.
Yeah. Yeah.
And the 2 points, the two endpoints of this path are both kind of limiting points where something becomes degenerate. In the Gromov-Witten theory, it's a large volume limit point, and I don't know what else becomes degenerate at the FJRW point.
Yeah.
But in the B model side, when we take the mirror of this, at one end you get the large complex structure limit point, which is again a very degenerate thing. But at the other limit, you're ending up at the point which is not degenerate in any way of the complex structure, at least. So I was wondering if there is any understanding why in the B model this is not somehow what degenerates at the mirror of the of the FJRW theory?
So that's a good question. I haven't thought about it that way. So maybe somebody else in the audience knows the answer to that question, but yeah, I don't know.
Well, I think it's also a limit point. In fact, it's kind of the so-called orbital point in the
Yeah, so the
moduli
exact
space.
point,
So
right? But I was
you're not in the middle. You're still in the limit.
But I was under the impression it was the same limit point, so I'm not understanding.
Yeah, it is a limit point.
Yeah.
Maybe
It is a limit point, but why is the orbifold point a limit point in any sense? Is there anything that's becoming degenerate there?
Oh,
well, this goes back to this paper of Morris and Plessel. I think that's discussed there a little bit. So some instantons. I think, yeah, it is a limit point. So I don't know.
is that Paul, by the way?
Yeah. Yes.
Hi, Paul. I don't
Hi.
see you, but I can recognize your voice.
Okay. Now maybe you'll see. Yeah. So that's my understanding of it. So.
Okay. All right. Okay, I'll have to look at that paper. I don't understand this well, but somehow, for example, if you're doing elliptic curves, one in the B model, one limit is the nodal cubic, which is clearly degenerate, but the other one is the Fermat cubic, which is still
complex multiplication.
It does have complex multiplication, but
Well, it's the same for the quintic. Yeah, but
right, but still the point is in the middle of the moduli space. It's not degenerate.
Yeah.
It's not in the middle. It's still a limit, but I mean, now what degenerates in the Ruan theory, that I don't know.
But yeah, but I don't get how is that different for going from matrix factorizations to. How is that different in the B model? You're saying you go to a different point for matrix factorization? I thought
No, you're going to the Fermat cubic.
Yeah, I thought it was the same.
Oh, okay. All right. But sorry, I don't understand. In the A model, it doesn't matter which cubic or quintic you take. It's the formation invariant.
Yeah.
Okay, fair enough. Thank you.
Yeah.
All right, let's thank David again. We continue at 1 p.m. Eastern Standard Time. Thank you.